Hello guys, so welcome back to our lectures. So in this lecture, we're gonna continue discussion about the transistor biasing circuits. We see many of them, okay? The last one we saw was the voltage divider biasing circuit. And here is another one. It's called self-biasing or feedback biasing, okay? You can see many names for it. So in this circuit, we have still one source, the VCC, not like the first one that we just take. It has two sources, one at the collector called VCC, another one at the base to provide the 0.7. But here we can provide the 0.7 basically from VCC, as we will see. Okay. So another important, comment here is that where is IC? So basically, usually we take, we used to make IC the current flowing in RC like this, but this is wrong. Remember, the basic definition for IC is the current that flows into the collector. Here is the collector. So this is basically IC, this current. And here is IB. So let's call this current I, the current that flows in RC. So I basically equal to, if we look at this node here, I is equal to IB plus IC. But wait a minute here. So we used to say that IE equal to IC plus IB, and here it is, I equal to IC plus IB. So this is basically IE. Then you're gonna say, how come? It's flowing in RC, right? Yeah, just to continue, draw the original circuit. In the original circuit, remember, we remove the battery and just put a node that carries the same voltage, VCC. This is basically the original shape of the circuit, okay? So look now at I. I is flowing in that direction, so it's coming from here, 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 here. Oh, it's IE. So that's, something, looks like counterintuitive. It's not counterintuitive or something, but just the naming that makes it a little bit confusing, because we name the resistance RC, although the current that flows into it is IE. Okay? Good. Let's see now how to analyze this circuit. How to get, the currents, how to get, the, IB, IC, how to get the voltages and so on. Okay. So let's start by, this equation that we just read, that I is equal to IC plus IB, which is basically IE. Okay. Another thing we should do is that we're gonna assume active region. So VBE is equal to 0.7. And of course, IC equal to beta IB. Okay. I'm gonna draw this circuit in another way. I'm gonna just take this wire, the VCC wire, and draw it in that loop here, okay, to make it easier for you. So for the analysis, I mean, of course, we can keep it like this and we still have loops and stuff, but it's easier to draw it in the other way. So let's do that. So we're gonna take this wire. I'm gonna just remove it from here and put it in the other loop on the other side of the circuit. So it will be something like this. And of course, this is ground. This is VCC. Why I did that? Just, to make this loop here clear. Although you can do the same loop if the wire on the right hand side, still the loop is valid. but it will be, more difficult to digest. Now it's a lot easier. You can, of course, move this, go, left and right, whatever you like, just wires. Okay. So let's, write down the equation of that loop. Okay, let's, assume any circuit. So VCC equal to IERC plus IBRB plus the 0.7. So you have here the 0.7, and you have here a voltage, which is IBRB, and you have here a voltage IERC. So that's basically, the voltages that you have in this loop. Okay, but remember, IE is basically beta plus 1 IB. So this is now the circuit loop. VCC is 10 volt. I just forget to put that in the, so VCC here is 10 volt. Okay, so if you look at that equation here, there is only one unknown. This unknown is basically IB. Everything else is known. So IB from that equation would be equal to 2.38 microamps. Microampere. Okay. Now we can calculate, of course, now you can calculate IC, now you can calculate VE. So IC basically is beta IB. You can calculate it very easily. Beta is known, 75. Okay, you can calculate IE as well. Beta plus 1 IB, 76 IB, and everything will be okay. Now the important part, to verify that we are really working in the active region. So VC, the voltage of that node here, is equal to VCC minus IE RC. So VCC is known, 10 volt. IE is known because we determined the IB. RC is known. RC is basically 4.7 kilo ohms. So from that, VC will be 1.486 volt. That's VC. How about VBE or VB? So look, VE is 0. Remember, VBE is, VB minus VE is 0. So basically, VB is equal to VBE, equal to 0.7. So basically, VBC equal to VB minus VC will be equal to 0.7 minus 1.486. This is basically something in minus, basically minus 0.78. So basically J2, the junction biasing between the base and the collector is reverse. And that approves our assumption. Actually, this circuit has another big advantage, really big advantage, is that it's really working all the time in active region. Okay, whenever you have a VCC, okay, of course, this VCC must be greater than 0.7. Okay, so whenever you have a VCC that is greater than 0.7, this circuit will be in active region. Okay, why I'm saying VCC must be greater than 0.7? Because basically this is the loop, this loop here that I just draw. This loop has VBE and VCC. So VCC here is the one that, provide this junction with its voltage, VBE. That's why VCC must be greater than 0.7. That's number one. But whenever you have this, it's always in active region. And why is that? In active region, we want this junction here, J2, between the base, this is the base, and the collector to be reverse or off. I'm sorry, to be off. It might be forward, but with voltage less than 0.4, as we discussed, many times before. Okay, and this condition is satisfied all the time here. I mean, if you wanna this junction to be off, one option is to make it reverse, right? To make VC, this voltage here, greater than VB, this voltage here. And that's basically the case. Remember, IB is flowing from that node, the collector, into the base, that node, flowing in that direction. For a current to flow, for example, between 2 points like this, in that direction and positive, and remember, IB must be positive, that node should have a voltage V1 greater than this voltage. So that the current flows from V1 and V2 become positive. And that's the case. So basically here, whenever VC is greater than 0.7, IB will flow from this point to this point, from the collector to the base, and IB is positive, so that VC will be greater than VB. When VC is greater than VB, that means the collector, which is N type, will have a voltage that is greater than the base, which is B type. So that's a reverse junction. That's why whenever this circuit is biased with a voltage VCC greater than 0.7, it's active all the time. It's very stable. If we compare it to the circuits that we studied before, other circuits, have, relatively unstable. If there is a change, for example, in beta, because beta changes with temperature, it's sensitive to temperature. So there might be a change, but here, no. The dependence on beta is really small. Okay, guys, that was basically the analysis of this self-biasing or feed biasing circuit. Thank you very much for watching this video, and see you in the next video. Bye-bye.